Well, the next thing I want to visit with you about is inclined planes. We talked a little bit about point masses on an inclined plane in Chapter 3. So we should be somewhat familiar with how to manipulate the free body diagram and draw the forces a little bit, but we haven't considered objects with shape and size and dimension. So in this section, what I want to do is contrast the normal forces at the tires depending on whether it's on an inclined plane or on a flat. So let's do the flat first. Alright, this is fairly easy. There's a center of gravity. It's located right here, 0.8 meters from that side and 1.2 from that side. So let's just find out what the normal forces are, the reactions at A on the flat. Alright, so we know there's going to be a force here. We have an mg. So let's do sum of the moments about A equals 0. It says the car has a mass of 1,500 kilograms, so minus 1,500 times 9.81 times 0.8 plus B times 2 equals 0. And so B here, the normal force at B, is going to be equal to 5,886 newtons. And we can find out the forces in the A by either summing the moments about B or summing the forces in the Y. So let's do sum of the forces in the Y is equal to 0. So I got A plus B minus mg is equal to 0, and so I can find A then is equal to 8829. Okay, those are the normal forces if it's on a flat. Do you think those normal forces would change if it's on an incline? Well, let's see what it is and see if we can figure that out. Alright, so now let's try to find out the normal forces of this car on the incline. So here we are with the car's position on incline. It's 30-degree angle, and so there's a force here caused by something. We'll say that's either a chalk block or maybe a brake or something like that, something to keep it from rolling down the hill. This doesn't really affect our problem too much at this point in time. When we get to friction, we'll be talking about what it takes to move up the hill and how much friction it takes. But for right now, what we're really concerned about is the normal forces. These are round wheels, and so there's a contact surface right here, so there's going to be a normal force perpendicular to the contact surface like that. And so here's our free body diagram. I got an A pushed up and a B going up like that. We have an angle here. This is the 30-degree angle, and so our rule is the angle that the incline makes with the horizontal is the same that the normal makes with vertical. So vertical is always going to be the mg, the weight always goes down. The normal force is the force that goes into the hill. And so in this case, mg, and that's going to be the angle theta included there, so that makes this mg cosine theta. And then this component will be mg sine theta. This is the same as what we did in Chapter 3. Now let's try to find out what the normal force is at A or B. Let's sum the moments about B first and see if we can find the normal force at A. Okay, if I do that, sum of the moments about B. First I got this mg cosine theta times that lever arm. That's going in the positive direction. Then I got mg sine theta times this lever arm, this small lever arm, 0.4. That's going in the negative direction. Minus A going also in the negative direction. It's got that 2 meter lever arm. And I can get A is equal to 61.74. Now is that greater or less than when it was on the flat? So if you can look at your prior page, you said A on the flat is equal to 8829. So clearly the force is much less on an incline. The normal force is much less on the incline than it was on the flat. How about B? Let's see what the normal force is for B. Let's scooch up here a little bit. I can do that in one or two ways. I can take another moment equation about B, or I can sum the forces in a direction. In other words, if I call this my direction, whoops, let's do this. I can call this a x prime dimension. This would be y prime dimension. So if I sum the forces in the y prime dimension, this is what I get. And so what I got there is mg cosine theta and b and a. That's what that's all about. And so I got b is 65/68. And what was b before? B was equal to b on the flat. Whoops, I got the wrong color here, but that's okay. B on the flat was equal to 58/86. So A goes down when it's on the incline, and B goes up compared to being on the flat. Anyway, that's kind of where we're going to go here. You can sum the forces in the action. You can find out that friction force or whatever that is at FB. But again, I said that that's not as much of a concern right now. What I just want to do is contrast how we use the components, and we're going to need those as we do some work here in Chapter 5.